So we are talking about the relative density. So as I said, the relative density is a special weight volume parameter used in, as I said, sandy and gravelly soils, and maximum void ratio minus the in situ void ratio. Void ratio, this E is the void ratio of a soil element, let's say, in the field. Typically we use this for field. So E max is the maximum void ratio of the soil in its loosest state. The minimum void is this void soil in its densest state. So E is the void ratio of the soil. So if I let's say a line graph, let's look at the void ratio. Is this line graph? If this is, let's say, minimum void ratio and this is the maximum void ratio, so this is the densest possible, this is the loosest possible. Let's say this is the in situ condition, whatever the E is. So if you look at the formula says this difference is E max minus E divided by the total difference is E max minus E min. So this is like a percent density kind of a thing. So dr varies from, obviously, from 0 to 1. So let's look at 0. So if E is equal to E max, that means the it becomes 0. E max minus E max becomes 0. So then 0 means loosest maximum. So void ratio corresponds to here in situ. So it's the maximum very loose state. This is the loose state, and this is the dense state. The loosest state and densest state. So if E is equal to E max, then this becomes 0 and the dr becomes 0. And if E is equal to 1, so that means E is equal to E min, so this is the densest state. Anywhere between 0 and 1 is your density. It's hard to see from the back. Alright, so let's see what we can do. I'm going to zoom in a little bit. Raise it up. Is it better? A little bit? Okay. Any questions about the relative density? Okay. Oh, I skipped this one. Let me just go back for a second. So since there is a relationship between void ratio and porosity, you can actually come up with this relationship very easily. That's what this is. So this could be a an exercise you might want to do. Now, what are the things that affect the relative density? Obviously, the grain size, grain type, grain size distribution curve, and materials passing number 200. Sometimes you will want to change the relative density of the, since there could be a minimum limit. I want minimum 90% relative density for a for a certain location. In that case, you need to keep in mind these are the things that you. Now, sometimes we would like to get very estimate of the maximum and minimum void ratio. These two equations are useful. Let's say if you want to estimate, let's say that somebody asks you to estimate the cost of a certain project, and you need to determine minimum and void ratio. In that case, you can use these two tables. Now, what I'm going to show now is you have the equation number 1. I'm sorry, equation number 2. I call this equation number 2. 4.3 is 2. And this equation number 1. There are 4 equations I know, but I call them equation number 1. So this table is essentially on the fines content, percent passing number 200 sieve, that's the F sub C. Depending on that, you choose one of these relationships. So you just need to choose depending on the FC. For example, if FC is 50%, then you have to use, this is a silty soil, you have to use this. This is equation 1. So let's say FC is 50%. Passing F means fines, finer than, typically finer than, okay? It's fine content. Material passing number 200 sieve. So if it's 50%, then we would be using this equation. We are in this row, so the equation would be E max is equal to 0.44 plus 1.32 times E min. This is number 1. The second equation is this. If I rearrange this equation slightly, E max will be 0.23 plus 0.06 divided by D50 E min. So this is now equation number 2. So you have equation number 1, number 2. You also obviously need the D50 of the soil. From this, you can 2 equations, 2 unknowns, which are E max and E min. You can solve for it. Solve for what? E max and E min. So these 2 unknowns can be solved, can be estimated essentially by knowing size distribution curve. So all you need the grain size. If you have the grain size distribution curve, you know what F, and also you know what D50 is. From that you can estimate E min, minimum void ratio, and maximum. This is just an estimation. It's the accuracy. You can see all this range. So it's not very accurate, but it is a good estimate for estimate. So is it clear how we use these 2? Okay. So what are the typical numbers for relative density? This table is typical numbers. If your relative density is between 15, we call it, this is a very loose soil. Anywhere between 15 to 35, it's a loose soil. 30 to 65 medium dense, 65 to 85 dense sand, and 85 to 100 very dense sand. Okay, so this is a typical classification based on relative density. Okay. Now we're going to move at Tyberg limits. As I did at the beginning of the class, with the plate on everything, based on the amount of water that is in clay. Now we are getting into clay. So we are switching from sand to clay, or clayey material, clay or clayey materials. Okay. Clayey means there is clay in it. Okay. So based on the water content, it can behave like solid, semi-solid, plastic, and liquid. So as you increase the water content, so let's just draw a line and we'll. So this is 0%. We are talking about moisture content, water content. Weight of water divided by weight of, any volunteers, divided by, is it total weight? It's the solids, S. Perfect. Did you know this was an interview question for me? Actually, I was being interviewed at one of the companies, and for soil geotechnical engineering companies, one of the questions was, technical question was, just tell me what the foreign water content is. Since it's kind of odd, right? So weight divided by weight of solids. It's not like the total weight. It's not volumetric either. So it's based on the weights. So obviously I answered. I got the job. I got that. So weight of water divided by weight of solids. So let's say if it's 0% pure dry clay. Now, as we add For dry clay, if it's really densely compacted, it will act like really a rubber. I brought the pieces last week. So it will be like solid until a point. So let's say semi-solid. And then L or W sub L, plastic limit. At some point it will transition from solid, semi-solid to plastic. Then at some point LL or W sub P, I'm sorry, this should be W sub P, plastic limit, W sub L, liquid limit, or LL. Different books, different people use different acronyms for this, but LL and PL, these are very, very common. So this is the liquid limit. So when the clay is between, when the water content of the clay is between the plastic limit and the liquid limit, this soil is plastic. We call it a plastic soil, like the Play-Doh you just saw. All right, that state is plastic state. It has nothing to do with the regular plastic that you use in the field. Okay, you know. Okay. Now there's a but here. So how do I define plastic limit? How do I define liquid limit? How do I measure? Okay. So that's one of the things that Tyberg did. So let's write it down. Liquid limit is the content at which soils like fluid. So after plastic we have or liquid. Liquid. When I say liquid, as I mentioned, it's like peanut butter liquid. If you call it a liquid, okay? But if you keep adding water, of course, it will be a lot more fluidy. Okay, so this is, I'm talking about just this transition at this point. Now let's write. Let me fill out these, and then we're going to talk about that device that I brought here. Now liquid limit is determined by using a lab apparatus here. So let me write by a crank operated cam. The cup is lifted and dropped from a height of 10 millimeters. Okay, we're talking about. And this is